Alrighty, good morning everyone. So, I guess today we're talking about standing waves. So again, let me kind of show you a little video here. So this is a simulation that kind of shows you what's happening. So I showed you a little bit, but this is going to show you actually the incoming wave and reflected wave moving the entire time as well. So let me show you that. So again, here we have one fixed endpoint at the end. As we talked about, we know that the incoming wave, when it then hits the boundary, then has to go to 0, its amplitude, and then it's going to send a reflected wave back. The reflected wave will be out of phase from the original wave, which will then interfere with the incoming wave to then create the standing wave. So this is our incoming wave, which is the total wave at the moment. Eventually it will encounter the boundary. Almost there. There we go. So now you can see the reflected wave now starting, and then you can see the total wave. So what's happening is you have a right moving wave moving the entire time, and then a left moving reflected wave, but then it's the interference between the two of those, which is actually creating the total wave, which is the standing wave. So this one here is the total wave. The red one moving to the right is the incoming wave, which is always moving. The blue one is the reflected wave, which again is always moving, but it's the interference between these two, which is then generating our standing wave. So we always have a right moving wave and always have a left moving wave, but the interference between the two of those creates the standing wave, where again the standing wave is defined by the fact that these nodes never move, they never propagate, they stay in exactly the same position. Which means that in space, what happens is this profile stays as a sine curve, and the only thing that happens is actually the amplitude changes as a cosine curve. So what actually happens is your amplitude becomes time dependent while the profile stays only the same in position space. So basically kind of want to put out here, I'm going to save most of the math for you. But what's happening is we have the total wave, which is being generated. This is our incoming right moving wave. This is our reflected left moving wave. And again, the only difference between these two is the fact that, well, this one is right moving, this one's left moving, hence the sign difference between the two. And since this one is out of phase from the original by 180 degrees, that means the sign picks up a negative sign. So here, if I use a trig identity, I'll save you the scariness of trig identities, but basically what ends up happening is this thing breaks down to twice the amplitude times cosine of omega t times the sine of kx. So what happens then is this wave, again, which is a harmonic wave or a traveling wave or a periodic wave, and so is this one, these two, when they add together, ends up separating the position and the time portions. Because here, again, in the traveling wave or the periodic wave, the time and the space are mixed together inside of the same trig term. As opposed to here, when it becomes a standing wave, what happens then is the time and the position split off into two different trig terms, which causes it to not be a traveling wave anymore. So this portion here basically acts as the new amplitude. So this guy we can call as some amplitude, let's say A prime. So what ends up happening then is this becomes a new amplitude A prime times simply sine of kx. But A prime is actually time dependent, because it's twice of the original amplitude times cosine of omega t. And that's what you're seeing here. So the sine portion is only dictating what this black curve looks like, which looks exactly like a sine curve. And then the cosine portion is actually dictating how these particles in the medium simply harmonically oscillate up and down. So what happens then in a standing wave is it splits up. So time and space split up into two different trig terms. It picks up then basically a time-dependent amplitude, which then causes it to only oscillate in time while this thing has a fixed sinusoidal profile. Now, this is true for example, the two fixed endpoints. Other examples we can have, which we'll talk about in this upcoming chapter, are we can have two open endpoints. In that case, the only thing that's going to be different is this thing looks like a cosine curve in profile as opposed to a sine curve in position profile. And then we still have the harmonic oscillation, but instead of this thing being a cosine curve, it becomes a sine curve. So basically, these trig terms end up just switching for two open endpoints. So, as we also learned yesterday, we know then that we can only spit certain wavelengths on the inside. My certain wavelengths are going to be twice the length divided by the harmonic, where the harmonic is any integer. You guys familiar with this? Z? No, just means integer. So this just means that it's 1, 2, 3, blah, 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 technically positive integers. And then that forces the frequency also to be fixed because again the velocity is constant, which is the same as the velocity, because again, as we talked about yesterday, this velocity of the incoming wave matches the velocity of the outcoming wave, or the reflected wave. So this is equal to the frequency times the wavelength, which means our frequency then is equal to the velocity divided by the wavelength, which means that this is going to be equal to the velocity times the harmonic divided by twice the length. So these are our standing waves. So I just wanted to explain that a little bit better, talk about this a little bit more. So again, what's happening is we still always have the right moving and left moving waves. They're still traveling waves, but the interference between these two traveling waves actually creates the standing wave. Okay? So that brings us to today's group exercise. This will be the end of this chapter. And we'll move on to bigger and brighter. So, today's group exercise has to do with standing waves. So this is the portion of a cello string between the bridge and the upper end of the fingerboard is 60 centimeters long. So let's kind of draw what's happening. So basically, this is the neck of the cello. Down here is the bridge. And then basically what's telling me is as my strings are going over the cello neck here, this neck is equal to 60. So this is the length of my cello, at least of the neck. So in this case, it has a string, and the length of the string has a mass of 2 grams. So we know is that one string which is going on here has a mass, and that mass then is equal to 2 grams. So this is the mass of the string. Right. So this says the string has or sounds a note, actually a 4th note, which has a fundamental frequency of 440 hertz. So we have an 4th note whose fundamental frequency F1 is 440 hertz. So now the question is basically saying is then where must the celloist put his finger or her finger to play a D5th note whose fundamental frequency is 587. So here we want to play a D5th note whose fundamental frequency is 587 hertz. So basically what has to happen is the celloist has to put their hand at some point. So put a finger on that string. 4 other fingers. Thumb doing the back. There we go. So we want to know where exactly does the celloist have to put their finger to create this particular note on this particular string. So basically we're asking then the question of how far away from the bridge must the celloist put their finger to play this particular note. So again, as they slide their finger down, they play different notes depending on the length of the string. So basically all they're doing is they're changing the length of the string, which then causes the fundamental frequency to change because the wavelength is changing because it depends on the length of the string. So this is what we want to know. We want to know then where must the celloist put their finger away from the bridge to then create the D5th note whose fundamental frequency is 587 hertz. Then part B is then saying, okay, without retuning the string, meaning that they're not going to increase or decrease the tension, is it possible for them to play a D4th note whose fundamental frequency is 392 hertz? So you have to answer yes or no, and then give a good reason why. Answer is pretty simple. Not too bad. So again, original neck is 60. Original string with its tension plays the A4 notes with the fundamental frequency of 440. Now you've got to figure out where they need to put their finger to then create the 587 fundamental frequency. So then, I'll have you guys break up into groups again. Discuss amongst yourselves. This walking around as usual, annoying everyone.
On there.
Oh yeah, probably. What's up?
Hi. Welcome to that.
All right. So you totally wrong. So it's asking my.
Did you start looking at orange?
No. So we can just change.
The frequency.
But it's like making sure, yeah, because that's the thing.
Yeah.
So what do you do?
Do we need to solve for V and then plug it into the V and LQL?
What'd you say?
We need to solve for V and plug it into the FN equals V and LQL.
Well, I was thinking like, for this equation, like the weight goes 2L over there. I'll put the 587 that we want in there. And it's the fundamental, so it's just Y weight. And then we solve for L, which is, I don't know if that's right, it's probably not.
You're close.
Okay, I was gonna say that.
I do need one more piece of information.
Okay.
Do we need the velocity?
Yes.
That's all.
So the velocity is wavelength times the frequency.
So can you
Oh, well, because if you look at this expression, right? So as you were saying, the fundamental frequency is the length, but you need the velocity because it's part of the expression.
Okay.
So you know n is equal to 1, you're looking for L, you know this, but you have two unknowns.
So how was I trying to do it with the top equation there?
Or
I was trying to
this
do
one?
up one.
This
I
one?
was trying to do, yeah, I was trying to put like the frequency that we want as like,
Well, because this is wavelength, not frequency.
oh yeah, my bad. That's missing.
So that's right. So to get the, so from here,
Gotcha.
to get the frequency,
Yeah,
or to get the wavelength from the frequency, we need to know the velocity.
gotcha.
So the wavelength would be the 2L, and then we could plug that into V equals the wavelength times the frequency that we have to solve for V. Would that work? Do the 2L to get the wavelength, and then plug that in here since we have the frequency to get the velocity of the first one.
Okay. And then what has to be true about the velocity from the
They have
440
to-
to the 587?
Just equal each
They
other.
have to equal each other. Good. Why? Doesn't make sense.
Why?
So why? Good.
What was the question?
So the question is, why does the velocity have to be the same from when it's played at the 440 to when it's played at the 587? So why does the velocity have to be the same?
Something with it being fixed.
Such a word. That's all.
That's superposition.
Not superposition, actually comes from before that. So if we go to the velocity of the string on a, or the velocity of a wave on a string. So let's look at that expression.
Was someone who's like the same medium?
Well, no,
Or something?
not quite the same medium, but close, kind of. So
If this one here, V1.
good. So we have V is equal to the square root of the tension divided by the
Oh, the
linear
radius.
mass density, right? So by moving my finger from here to here, am I changing anything about the tension or the linear mass density? No. The only way I would change the tension is if anybody plays guitar, when you like bend the string, right? So when they, you know, especially guys who like to play solos, right? And they get it to scream there, they're bending the string and they're causing it to move, which causes the tension to change, which causes the pitch to change. So in this case, by me just moving my finger from here to here, I'm not changing the linear mass density because that's property of the string itself, and I'm not changing the tension because all I'm doing is just cutting on off at that point. I haven't changed anything about the tension. So So that's right. So since I didn't change the tension and since I didn't change the linear mass density, the velocity has to be the same. Correct.
So you do the wavelength for part one portion. Do 67.
How are we doing over here?
Wavelength 2 times 65.
You did it 2 times what?
So how do we do it?
2 times L.
Oh, the 0.6. Okay.
And how do we
And then we can solve for
Okay.
V. And they gave us the
And that gives you the
frequency.
velocity. Good. So be careful. That's in. So right now you're.
So the 440 times 1.2. Okay.
Oh, and then you put it in a meter. Okay. Okay. So that's 1.2 times. Okay. Good.
440.
Okay.
So that,
So you're using the
that's
fact that
the
the
velocity for the first one, so V1 equals.
So why is that true?
So B for the next one would have to equal 520, and then I think we can solve for.
That's correct. Good. And
Since
have
we
you
have
changed any of the local properties of the
For
string?
the
So remember that
frequency.
the
Yes,
velocity
solve
of
for
a wave of string only depends on
I
the
guess we
tension.
could solve for a wavelength, and since we have that, then we could plug it
And
in
then
and solve
change
for
it.
the
That's
length.
right. So just moving my finger from this.
Yeah,
way
because that's what I'm trying to do. I
changes
just did mix the terms up. Yeah, you're right.
The only way I would change the tension is
528
if I bend the
equals
string. Or tighten. That's right. Or like a guitar player.
wavelength and the frequency V5 is 587.
Causes the frequency to change because they're changing the tension. So exactly. So then exactly. So going back to there, so now you have 587 is equal to 0.80 divided by 2
what you got.
times the length. You're looking for the length. And then
Oh,
you solve
yeah,
for
trust
the
your
length. So
calculator.
the length.
Oh, okay. No, I wouldn't do that. I wouldn't trust any of my stuff.
Whatever the velocity was
We'll go.
divided by
Okay.
twice.
So then-
587.
And then plug that in. So we want to solve for M. 0.
And it's the fundamental, so that's just 1, correct?
2
So we should have the velocity, which was what, 528? There you go. So it's 528 divided by 2 times.
Yeah.
0.45 meters.
587.
Times it back by 100. So
There you go. So that's
24.5.
about 45 centimeters.
Let's call game.
Did you do that right? So once we solve for V1, we know that V2 has to equal that 2, and then solve for lambda, and then plug that into this one to get the length. The second part.
yeah, you can do it that way. Or when you get the velocity, you can just plug it right back into the other,
Oh.
the frequency one, so.
Oh, I forgot about that one that I actually wrote down.
Wait, what was it?
You can plug it into the VN over
Plug it
to
right into there and just rename LX or something, so.
just one extra
It
step,
is
it's
the-
fine.
It is the 1 because it tells us that's the fundamental.
Correct, okay, exactly, yeah, so in both cases, it's just the fundamental.
So if it said like second harmonic. then we
If it
know.
said second harmonic, then it'd be n is equal to 2, or if it said the D fifth note on the third harmonic, but that's right. Yeah, so when it says the harmonic, it's telling you what the end value is. Exactly.
And then for B, could we
Oh, yeah,
just
for
try to
B.
plug in that 392?
Yeah, so do the same thing, plug in 392 this time.
Into that one?
Well, so you're doing the same thing as you did down here, so the velocity is still the same. So now you're just changing out, and you're doing 392 is equal to that velocity divided by twice the length. And now just solve the length again.
Yeah. And what?
2 times the length.
I'm sorry.
So I think we can just solve for one.
Right, frequency is smaller, which means what has to happen to the length.
So
Is that big? Because it's inverse proportional.
Listen, this is like without returning, to get away here, the length is the same though.
So what happened is actually the length is greater than the length, you know.
Is it asking not returning to A4 or not returning to,
Correct, yeah, which is
Well,
greater than the size.
I guess it would be A4.
And that's why you can't do it. Unless you
Right.
grab it and act it.
Yeah.
Yeah, I mean, if this person's really good at guitar, I guess they can find a way.
How'd it go?
Where are they starting at? Like, without returning?
So they're starting at the D5,
Are they starting?
Well, it
at
doesn't matter where they start.
but without returning to where?
No,
Original
without
position?
retuning.
Oh,
So it's
Oh, I thought it said returning, so I thought it was, yeah, okay, I was wondering, like, so they're keeping their hands the same spot, and then they're like trying to, okay. I mean, I was just gonna say no, but depends how good they are, how long they've been playing.
but we should solve for L and make that
Yeah.
determination.
Yeah, so you're just resolving for L, and then just seeing this L compared to the original L. Exactly.
Oh, okay, and then seeing if it's like longer than the 60, or if it's in that range. Okay. Yeah.
So if it's longer than 60, they can't
Yeah,
do that.
need the guitar.
Unless you
Sure.
stretch the neck of the guitar.
So
Yeah.
L is 528 divided by 2 times 6, 7.
After you do that, do you ever see your math on that, what you did? So I know we're resolving.
So use that equation to solve for L. The velocity should remain the same.
Okay.
Cross multiply the 2L with times.
Yeah, so you're still using this, you just derived it out to get solve
Yeah,
for
I
L.
did.
Okay, gotcha.
And so what's the story there? It would be too far away. Oh, it's only 60 centimeters long and we got 67, so it would go off of the instrument. So the answer is no. The string is only 60 centimeters long.
That's a fun one. I feel like we've got like better these things like every single time.
Oh,
First time I was confused. And then
I was
second time,
confused.
we did a lot better than this time, I think.
It's hard seeing like you're already knowing the answer and trying to figure out where'd that come from. Now I have to work backwards.
Yeah, now we, yeah.
Nice.
Yeah, you had it about done the first day you came in.
I know,
was like,
I
all right,
started
all
to do
right.
it a little bit. Not to waste my time on these at home if I was gonna have to come in and do them anyways in class.
Yeah. Did you go like that?
What's 57? So I guess
Okay, yeah.
technically I'm from Hofstadt, but
Yeah.
nobody knows where that is. I just say Evansville.
So what year
I
you
used to,
I'm
Or you
I'm going to be
Hofstadt.
a junior.
So you.
Oh, it's right on the syllabus.
my grandparents live in Fort Branch. I have a cousin
Oh, the
that
access
lives
code,
in
yeah.
Southern. My brother was there for a
It
while.
should carry over. Oh, the Coast Guard, yeah, that's right on the syllabus itself. So if you go on to.
Really? Who?
Yeah, it was a long time ago. Well, she's like 27. It was open pile of water.
That's a long time.
So you go under our Blackboard page. And then just under syllabus.
Yeah, I graduated high
Just
school.
right on the bottom.
Where'd you go?
I might know him, actually.
Did you go to?
I went to North
Okay.
Evansville, the old North.
Not the solar panels on the top door.
Nope, the one that's like a disciplinary school now in Sherringtown. They took the old school and just turned it into some intermediate learning school.
All right, so it sounds like everybody's done, so that's good. So
Big.
let's
We had a really nice theater.
move on to the new chapter. So that marks the end of chapter 11. So now we're gonna move on to chapter 12. So chapter 12 basically deals with all of this wave stuff that we've been talking about, except it uses it for one particular type of wave, which is called a sound wave. So basically we're just gonna talk about sound waves in this chapter. So sound waves. So how does sound work? So basically, when we think about sound, as we talked about, sound means some sort of medium for it to actually travel through. So again, you hear me talking to you in this room, sometimes more than you'd probably want to hear me talking, because I'm creating pressure variations in this room. So basically what happens is when you first walk into this room, on average, we have air molecules moving in all different directions. They're moving on average the same, and they're all at basically the same pressure. But when I start talking or start clapping or making some sort of noise, I'm then creating pressure overages and underages. So basically what I'm doing is when I clap, I'm causing all the air molecules in this region to push away, which then causes them to move into another location, which causes basically a whole bunch of air molecules to be on top of each other, causing larger pressure. Nothing wants to be at a high pressure, it wants to move to a smaller pressure region, so it'll start to expand away, hitting the particles next to it, causing them to move into overpressure areas, causing them to move away, causing that to go to an overpressure area, and then so on and so on, which then causes my sound to go to you. And as we talked about, what happens then is what the air molecules themselves are vibrating, your eardrum then picks up that vibration, and then your brain transmits that into some sort of sound. So physically, this is what's happening. So here I have some sort of, say, speaker. This is then creating my pressure overages and underages, which then is causing these air molecules to start to vibrate. But as you can see in here, the air molecules themselves are only harmonically oscillating back and forth. But the wave is then traveling along this direction, which makes it a longitudinal wave. So from some terminology, wherever I have a overage in pressure, say this portion here, which is traveling like this is what's known as a compression. So when I have a high portion of air molecules compressed on top of each other, this is called a compression. When I have a smaller section here, which doesn't have a lot of air molecules, this is what's known as a rarefaction. So underage of pressure versus overage pressure. Overage pressure is a compression, and then we have a rarefaction. So again, here, as this thing is traveling through, air molecules here, here. So this section here is what's known as a rarefaction. And this is what's known as a compression. This is sound waves. Now, when it comes to sound waves, there's actually two different ways we can describe a sound wave. So one way we can describe a sound wave is by pressure variations. The other way we can describe a sound wave is actually by the displacement of the particles themselves. So displacements. So we can either talk about it as a displacement wave or as a pressure wave. What can't you read?
Can you say that, is that just refraction or rarefaction?
Rarefaction.
Rarefaction.
R-A-R-E fraction.
I got it, just gonna
There we go.
That's like nothing's.
It's not like nothing, but it's a low kind of pressure.
Not a
Yeah,
lot.
so there's basically absence of particles. Yeah. So the maximum absence of particles. So if you think about a transverse wave, for example, it would be this location of the transverse wave. So basically, if there was a transverse wave, this would be the location of the rarefaction. And then this would be the location of the compression. Usually transverse waves, we call this a what? Trough and a crest.
Mm-hmm.
So this would be the crest. This would be the trough. I can't spell. Have we gotten used to my chicken scratch handwriting yet? So again, these particles move. These are a longitudinal wave because the particle is oscillating back and forth in the direction in which the wave itself is moving. The wave propagates again by the fact that I'm creating these overpressages. They're moving away. Overpressage, move away. Overpressage, move away. Compression, rarefaction, compression, rarefaction, which causes it to move away. So again, we can describe this one of two ways. We can either describe it as a pressure wave, which in this case we're actually describing as pressure variations above the average pressure in this room. So again, if I was thinking about this room, and so here's my room. On average in this room, I have an average pressure, let's call that pressure P0. Now when I create the sound, I'm actually then creating a pressure fluctuation over top of that, which means I'm creating a small amount of pressure delta P. So here I could actually then describe the pressure, and then delta P then is equal to the average pressure, in this case, times then cosine of omega t plus or minus k times x. However, we can also think about describing it as a displacement wave, which means we can talk about how far away each one of these particles are displaced from its original equilibrium position. So again, if I'm watching this red one here, this guy's oscillating back and forth about some equilibrium position. So I could instead describe this in terms of that displacement. In that case, we usually say that the displacement S is then equal to the amplitude Sm times, in this case, actually sine of omega t plus or minus k times x. So it turns out that it doesn't matter which one of these I actually use to describe the motion of the wave, but the only difference between the two is that, well, one, the amplitudes are related to each other, but not exactly the same, and two, notice these guys are actually out of phase with each other. The reason for that is, so if we look at here, what happens again, where I get a compression, that means all the particles are pushed into this one location, which means when I have a maximum pressure, I have a zero displacement. So when I have maximum pressure, which would be in these locations here, I'm pushing all these particles together, which means that the particles which are in the center haven't moved away from their equilibrium position. So when I have maximum pressure, I have minimum or actually zero displacement. But then when they move away from each other, so when I go from the high pressure or the compression out to a rarefaction and they start to move away, they have maximal displacements, but I have zero pressure in this case. So again, whichever way I define or decide to describe these, it doesn't matter. These amplitudes are related to each other. But the only thing that's different, again, is that they are 90 degrees out of phase with each other. So when one is a maximum, the other one is at zero, etc. But ultimately, it doesn't change the math. So the angular frequency of the pressure is the same as the angular frequency of the displacement. The wave number of the pressure is the same as the wave number of the displacement. So all the information is the same, except, again, they're out of phase with each other, and the amplitudes are slightly different. Okay. Now, the velocity at which sound moves in air is a little bit complicated. It turns out that the speed at which sound moves in air depends on multiple things. It depends on the density of the air, it depends on the humidity of the air, and it depends on the temperature. And atmospheric pressure and all kinds of other different things. For us, we're just going to say, well, it only depends on temperature. So it turns out that the speed of sound in air is equal to 331 meters per second times 1 plus 0.6 times the temperature in degrees Celsius. This is the temperature. So this is the speed at which it travels. Yeah, hold on, I don't remember. Oh, sorry. There we go. Okay. So it's actually 331 plus 0.6 times the temperature in degrees Celsius, meters per second. Sorry. So that means that what? At 0 degrees Celsius, the wave travels at 331 meters per second, but then as the temperature increases, the speed of the wave actually travels faster. Which is why yesterday in lab I said it should be somewhere between 331 and about 345 because it depends on the temperature. So to really know what the speed is going to be, it does depend on the ambient temperature. But yeah, it's a little more complicated than this. It does depend on other things too, the density of the air, the humidity, and all this different stuff. But we're only going to say it depends on this.
So then you can use like velocity of sound to find the known temperature.
You could, yes, exactly. Exactly. Yeah. Okay. Now, as far as us being humans, we only hear certain ranges of frequencies of sound. Now, technically, sound can have a frequency going all the way from 0 all the way up to infinity, But us as humans, we have a limited range of frequencies that we can actually hear. Turns out, for us humans, we can only hear from about 20 hertz up to about 20,000 hertz. So now, this is a person of good hearing can usually hear about this range. Other people can't usually hear all of these different ranges, like old people like myself. People who have had a lot of, especially when you're a kid, had a lot of ear infections. That usually damages a lot of the inner ear, especially the hairs in the ear. People who have a lot of sounds around them all the time. So people who work outside, especially in construction. Myself, I used to play in bands when I was a kid. Especially my hi-hat. I used to play drums. I cannot hear that pitch at all anymore. So that is great. But let's test your hearing. So let's find out. That's not full notes. Can you hear that? It's like a heartbeat, especially if it's a heartbeat. All right, do some intermediate range. Okay, with those, good. You still hear that? I'm done. Still okay? I can't really hear that. You still hear that? Still hear that? Still hear it, Glenn? No. Okay. So that was about, again, about 20,000 hertz for you guys. I was done about 15,000. So enough of that. So anyways, so we have a limited range of sound that we can actually hear, at least for frequencies. Animals usually have a further range that we can hear. So for example, the dog can hear anywhere from 20 hertz up to about 45,000 hertz. As opposed to us, we can only hear about 20,000 hertz, which is why a dog whistle, for example, we can't hear, but a dog will go insane because it's in that frequency range that we can't actually hear. So not only can we not hear only certain frequencies, but we can also only pick up sounds when it has reached a particular intensity. So the intensity of a wave is basically related to the amplitude squared. So the intensity of the wave, so I is equal to the intensity, is proportional to the amplitude of the wave squared. So for most people, the lowest amount of intensity that they can actually hear is what's known as the threshold of hearing. Which we're going to call I0, which is about 1 times 10 to the minus 12 watts per meter squared. So this is what's known as the threshold of hearing. So the threshold of hearing is the minimum amount of intensity that we hear of a person of good hearing, of course, could actually pick up. Now, what we interpret then as sound level, so sound level intensity, roughly goes as the logarithm of the intensity. This is what we call a decibel. So decibel is basically how loud our sound is. So how loud is our source here. So it turns out that the sound level intensity, which we're going to call beta, is equal to 10 decibels times then the log base 10 of the intensity of the source divided by the threshold of hearing. So this is what we call the sound level intensity. So beta is the sound level intensity in decibels, which again is equal to 10 decibels times the log base 10, then the intensity of the actual source divided by this threshold of hearing. Now, one other thing that we know is that what? The further and further I get away from the source, the lower and lower and lower the intensity of the sound becomes. So, how does that work? So let's talk about the distance dependence. So let's say I have some sort of source here. So this is my source, S. And let's say this is giving off sound in all directions equally the same. So this is what we call isotropic source. Isotropic. Simply this means that equal amounts in all directions. My sound here is going off in all different directions. So basically what happens is as the sound moves out, the sound then creates spheres of some sort of radius of r. So imagine that my sound wave is moving out. This is the crest of the sound wave. You have a three-dimensional sound wave moving outward. So the sphere is the crest of it, or the compression, I should say, as it's actually moving away. So as this thing moves away to some radius of r, what happens then is that inside of here, this contains some sort of power, which is then generated by the source itself. So remember, power is the energy per unit time. So my source is giving off sound waves moving away with some sort of energy per unit time. All of that power then is contained within inside of the sphere. Now, as this wave starts moving further and further away, because we know the wave is moving outward with some velocity of v, depending on the temperature, the further you get away from this source, then the bigger the sphere becomes. So this is now my sphere at this stage here, which is at some other radius. Let's call this R2. Let's call this guy R1. Now, what's true though is since the energy per unit time is dictated by the source itself, what that means is that the power here is exactly the same amount of power here. But what is different is that if I was standing here this close to the source, versus if I was standing here a further distance from the source, the amount of the area that I encounter from this particular sphere is smaller here than what it is here. That kind of makes sense? So basically, what's happening then is as the source moves away, even though this sphere still has the same amount of power, it's still containing the same amount of energy per unit time, but the amount of the size of the surface area of the sphere that I encounter is getting smaller and smaller and smaller the further and further I get away from it. Which means that I'm only sampling a smaller and smaller section of this amount of area. So from here what we can then say is that my intensity at any point, so I will be intensity at any point, is equal then to the power, which is radiated by the source, divided by the cross-sectional area, or the surface area, I should say, divided by the surface area of the sphere. So this is then equal to the power contained divided by the surface area of the sphere. Anyone know what the surface area of the sphere is? What's the area of a circle? Good, so it's not that, but it's the surface area. It's related to that. There's a pi r squared. So we'll write that down. actually have 4 in front of it. So the surface area of the sphere is actually 4 pi r squared. So this is the surface area of my sphere. So this is my intensity. So this is how my intensity actually falls off as I move further and further away from it. So what this thing says then is that what? The closer I am to it, the greater the intensity, but the further I get away from it, the intensity falls off as 1 over r squared. And again, the reason for that is the power is contained the same within inside, but as I move further and further and further away, the amount of area that I encounter from the surface area, which has the entirety of the power, gets smaller and smaller and smaller, which means I'm sampling a smaller and smaller amount of that particular area. Meaning I'm sampling a smaller and smaller amount of the power contained inside of this sphere. So if I plotted then the intensity versus position, this thing is going to do something like this. So this is the intensity versus the distance. The further I get away, the smaller amount of intensity I encounter. So let's use this and let's do an example. So this says that the intensity of a sound wave from a jet airplane as it is taking off is about 1 × 10⁻² watts per meter squared at a distance of 5 meters away from the airplane. So then it wants to know, what is the intensity of the sound wave that reaches the ears of a person standing a distance of 120 meters away from the airplane? So let's draw. So here's my airplane. Well, the only thing I can still draw my whole page. Okay. So this thing is about ready to blast off. So here's all the air coming off. Right? So what we're told then is that somebody over here who's standing 5 meters away from this guy. So this is my distance. Let's call that R5 equals to 5 meters. Here's an intensity. Let's call that I5, which is equal to 100 watts per meter squared, which is the same thing as 1 × 10⁻² watts per meter squared. So we're just looking at this intensity. So now what I want to know is, if I take another person and I put them some further distance away, right over here, so that this person is this distance away, let's call that R120, which is 120 meters away. I then want to know, what is the intensity of the sound that this person hears? So this is what we're going to know. So what is my intensity of my sound? So how would I do this wrong?
D for salt for power.
Good! Because what has to be true about the power here versus the power here?
Be the same.
It has to be the same, exactly. So what we know now is that the power contained in the sphere here versus the power contained in the sphere here, as Christian said, has to be exactly the same. So what we can do is we can use this scenario here, using the fact we know the distance and the intensity to find the power, and then plug that into here to then find the intensity, because now we know the power and the distance. Exactly. Good, so let's do that. So let's look at, we know I5 is then equal to the power divided by 4 pi r5 squared. From here, this means that the power then is equal to what? 4 pi r5 squared times I5. I'm going to leave it like that because I don't like numbers. Okay? Now here, I also know that I120 is going to be equal to the power divided by 4 pi r120 squared. But from here, I know the power is the same thing as 4 pi r5 squared times I5. So let's put that in. So it's become 4 pi r5 squared divided by 4 pi r120 squared all times I5. What happens to the 4 pi's? They cancel. So finally what I get then is that the intensity at 120 is the same as the intensity at 5 times the ratio of the two radii squared. Okay? Plug in numbers, so this is then what? Again, 100 watts per meter squared times then 5 divided by 120 quantity squared. So plug in my numbers, what I find this case then is 0.179 or something like that. 174. 0.174 watts per meter. What's up, Quinn?
Okay, real quick, why did you put the I5 to the side and not divide it by the 4 pi r 120 squared?
Oh, I mean, I could.
Oh, okay.
It's just multiplication. So
Okay.
whether I moved over here, keep it on top, it's the same. So yeah. No, I mostly just wrote it that way so that way you can see that these guys cancel and just this becomes a ratio of the radii. So I was just being a turbo nerd. That's basically. Math excites me.
I was gonna say, you do like algebra. though.
I love that. Yeah. Want everybody to share in that. Usually a dying
I
call.
like to do.
Yeah.
Especially trying to convince biology majors all the time they should love biology or algebra.
Yeah.
Like, no, I'm never gonna see that again. It's never gonna. Okay, so everybody's okay? Not too bad, right? Not too bad. Let's do another one. So this one says, and we have, that's number one. Okay. Sorry, I don't have a slide for this one. Apparently, it just went away, so I'm just going to write it down. So this says that we have a source of sound has a power of 1 microwatt, and then if it is a point source, what is the intensity 3 meters away, and then what is the sound level intensity in decibels at this distance? Good. So what this says is that we have a source. Okay, so here's my source, which has a power of 1 microwatt. Everybody know what micro means?
So I think it's
That's right. So this is 1 times 10 to the minus 6. So this is 1 times 10 to the minus 6 watts. Good. So what we want to know is if I go some distance of 3 meters away, so this is my distance r equals to 3 meters away, we want to know then what is the intensity at this point, and we also want to know what is the sound level intensity. So what is the sound level intensity in decibels? So these are the two things that we want. So good. So how would I do this problem? Let's find the intensity first.
you can just go right ahead and solve for intensity.
Exactly. So here, we know the intensity, then it's going to be the power divided by our 4 pi r squared. Exactly. So it's going to be 1 times 10 to the minus 6 watts divided by 4 times pi times 3 meters watts of squared. A nice plug and chug question. So plugging in my stuff, what I get then is that this is 8.84 times 10 to the minus 9 watts per meter squared. So now we want to know what is the sound level intensity. So what is beta? So we now know that beta is equal to 10 decibels times the log base 10 of this guy divided by the threshold of hearing. So the sound level intensity then is going to be 10 decibels. Times then log base 10, the intensity divided by the threshold of hearing. So plugging our numbers, this becomes 10 decibels times then log base 10 of 8.84 times 10 to the minus 9 divided by 1 times 10 to the minus 12. Use my calculator, what I find is this works out to be about 39.5 Always going to be 10 to the minus 12. Yes.
I think I wrote that down wrong, then I had to the negative 2.
Yeah, so that would always, as long as we're human, it'll be 10 to the minus 12. But I only know it for humans, so it's going to be 10 to the minus 12. I'm sure other animals hear it lower than what we hear. Okay.
I was running something down. Where did the 10 to the negative 12? That was that part of the question.
Well, that was because remember decibels is always in reference.
Oh, IOs. Yeah.
I-
Okay.
Yes, correct. Yeah, so that's sound level intensity. Okay. Okay. So the last thing we're going to talk about today, we'll probably pick this up when we come back as well, is what's known as path length difference. Path length difference. So it turns out that since sound is a wave, and we now know based off what we talked about yesterday, that we can actually create new waves by interfering waves. So that means that sound waves can actually interfere with each other. And as we also talked about yesterday, the way that they interact with each other depends on when they meet with each other. So are they meeting out of phase with each other or in phase with each other? If they meet in phase with each other, that allows for the two amplitudes to add together, which creates constructive interference. And if they interfere out of phase with each other, that causes the amplitudes to subtract from each other, which causes destructive interference. So it turns out waves can actually do the same thing. So waves, or sound waves, can interfere constructively and destructively. So this means that if I have, for example, two sources, so here's source 1 and source 2, each one of these are giving off sound waves, which means we have those spheres, again, propagating out away from the sources. When these spheres now start interacting with each other, depending on if these guys are in phase with each other or out of phase with each other, will then create locations of both constructive and destructive interference. Which means that when I have these things turned on here, turn on to where I'm not going to blow up your ear. For example, if you walk around this room, now it's a little bit difficult in this room because we're also getting reflections off the wall, so the sound wave is hitting the wall and bouncing back, which is causing different locations. But what you'll notice is, actually, if you moved around the room, you would find locations where you hear the sound very high. It has a large sound level intensity, a large beta, large decibels. In other cases, as you move around, the sound level intensity gets smaller and smaller and smaller, and then in theory, if I didn't have the walls here, I would have actually locations where I would hear nothing. So I would go from nothing up to a maximum amount of amplitude, down to nothing, back to a maximum amount of amplitude. Which means that as I walk around this room, there would be portions where I would hear nothing and other portions where I'd hear maximum amount of intensity. And this is actually a huge problem when you think about things like amphitheaters or going to operas, places like this. Because what would happen? People pay a lot of money to hear somebody sing, for example. So here was the stage, and here's my person who was singing. Or I don't use microphones, but whatever. So here's the audience down here. If you've ever been to a nice amphitheater, what you'll actually notice is the room itself, or at least the walls and the back wall, are actually curved. And the reason for that is actually to get rid of this. So what happens is, if I had a flat wall, what happens then is as the person is singing, I get reflection of the wave going back, which means that somewhere in the audience, you would actually have locations of total constructive interference, some locations of destructive interference, which means some people who are paying a lot of money wouldn't hear much, and other people who are paying a lot of money would hear a lot. So what they usually end up doing is they make these curved walls, because what happens then, and we'll talk about this more later, when the wave hits the wall, it reflects off at exactly the same angle at which it came in at a 90-degree angle perpendicular to here, which means the wave would come in, hit here, bounce off down into here, which then the reflected wave would not go into the audience, which means that everybody would hear the same sound level intensity. This also happens in movie theaters. any place that you have sound. We'll do a nice example of this.
What do you think I did? I discreetly slipped off the other ear and put it in my pocket and then got the hell out of there.
I have a bone to pick with you.
Hi, Sheldon.
Hi, Stephanie. I'm sorry I'm late, but your companion left the most indecipherable invitation. What invitation? We're going to the movies. What movie? What theater? What time? If you were trying to make it impossible to locate you, you couldn't have done a better job.
Oh, clearly I could have.
It took me nearly 20 minutes to go through the browser history on your computer to see what movie times you looked up. Wait here, I'll find the seats.
Oh, no, we have seats.
Not the right seats.
How? What is he doing?
It's finding the acoustic sweet spot.
How? Does he always do this?
Sometimes he brings a toy xylophone.
Hold! Hold!
I am really sorry about this.
Oh, it's fine. How sweet.
My apologies, you've been sitting in it all along. But did you want to slide over one? No, just sit here.
Oh yeah, this is it.
It's time to.
I was gonna ask you if you watched Big Bang Theory.
I haven't in many years, but I used to love it when it first came out. I watched maybe the first 2 or 3 seasons.
One lady is actually a real neural physicist.
What's that?
One of the actresses on the show is actually a neural physicist in real life.
Neurobiologist, actually, but yeah.
Well, she said physicist in an interview. So,
Is she?
yeah.
Neurobiologist, but that's okay. Yeah, that's Blossom. When I used to play Blossom many years ago. Something. Anyways. So that's actually what Sheldon is doing here. So what he's doing is he's moving around the room, causing noise and annoying everybody, but he's trying to find the location where, as we were talking about here, since it's a square room, he's looking for where the reflections are coming back to create a location of maximum constructive interference, which gives them the loudest amount of noise. So it turns out that we can actually determine the locations of these constructive and destructive interference locations based off of what's known as path length. So we can actually determine all of these locations of maximum constructive interference or all these locations of maximum destructive interference based on the distance that the wave has traveled from each one of the 2 sources. This is what's known as path length difference. So path length difference then describes the location constructive and destructive interference. So how does this work? So let's say I have 2 sources. So here's source number 1, and here's source number 2. And let's say I'm looking at this location here. So this is the location I want to look at. So we then say that the sound from this one has traveled this distance here. So I'm going to call this distance D1. And then I'm going to have this one has traveled this distance from here to here. And let's go ahead and call that guy D2. So the path length difference then, we're going to call that delta D, is then equal to the absolute value of D2 minus D1. Now I'm only putting an absolute value on here just to make sure this thing is positive. Because it might turn out that D1 is greater than D2, which means it will end up being negative, so I just want to put that on there. So if this is equal to an integer multiple of the wavelength, this then gives us constructive interference. But if it's equal to a half integer multiple of the wavelength, this leads to then destructive interference. certain things I'm assuming here, I should probably point out, is that I'm assuming that the frequency of the two sources are the same. So just like we had here, these two speakers, which is the same thing when Sheldon is making that noise. He is the generator, but what's happening there is he gets the reflected wave, so the reflected wave is acting as the second source. And one other thing I'm assuming is that these two waves are originally in phase with each other. So that the wave which is coming off from here is exactly in phase with the wave which is coming off of here. If that's not true, these two things switch. So what happens is that this becomes destructive interference and this becomes constructive interference if they're originally out of phase with each other. But here I'm assuming that they're originally in phase, so this is true. So all this means is that what? If one wave has traveled this distance, another wave has traveled so that the total distance then is like this. So it comes in doing that. So it has actually traveled the distance of two wavelengths. The two waves come in so that they're in phase with each other. So the addition of those is added together, which gives us constructive interference. So whether I have another wavelength on here or another wavelength on here, as long as it is an integer multiple, they'll always be in phase with each other by the time they arrive at that point, which means that I get constructive interference. That's what this one is saying. This one says, well, if I take one wave and I shift it by half a wavelength, what happens in that case? Well, if I take this wave and I shift it by half a wavelength, what that means is that this wave is coming in like this. I've shifted it by half a wavelength, which means the two waves are now completely out of phase, which then leads to destructive interference. So as long as they arrive a half an integer wavelength out of phase, which means I shifted it by half a wavelength, they will be then destructive interference. M here is just an integer, which means M could be anything from 0, 1, 2, 3, blah, blah, blah. So it just means how many wavelengths are these guys traveling or out of phase with each other. Okay, so it's called path length difference. So again, path length difference says that we can describe the location of any of these constructive or destructive interferences only maximum to then learn the location of where these guys are going to be. So let's use this. Let's do one example. Other example we'll do next time, because that was a long example. So let's go back. Yeah. So good. So this says I have two speakers, both which have a frequency of 171.5 hertz and are in phase with each other, are separated by a distance of 4 meters. Now I'm going to take one of you guys, stick you in front of one of these two speakers 1.5 meters away from the speaker on the left. Then what I'm going to ask you is, are you going to hear constructive or destructive interference? And we're going to take that the speed of sound in air is 343 meters per second. So let's draw our picture. Let's see what's happening. So I have my two speakers. So it's like here's speaker left, and here's speaker right. These guys are separated by a distance of 4 meters. Here's my 4 meters. Each one of these two guys has a frequency. That frequency is 171.5 hertz. And we're told that the velocity and the speed of sound in air is 343 meters per second. A variation of this is I would tell you what the ambient temperature of the air was, and then you'd have to calculate the velocity that way. But only one more step. So now I'm going to take one of you. Who haven't I picked on in a long time? I'm going to go with Jasmine. I'm going to go Jasmine. Where's Jasmine? My artistic stick figures, great. And I'm going to put Jasmine so that she is a distance of 1.5 meters away from the left speaker. Okay. And what we want to know is, how annoyed is Jasmine going to be standing here? Is she going to hear constructive interference or is she going to hear destructive interference? So this is what we want. We want to know, is Jasmine going to hear constructive or destructive? So which one is she going to hear? Constructive or destructive? So how would I do this problem? Good, so let's start off with path length difference. So here, we know that our path length difference, delta D, is going to be equal to, so let's call this our distance D2, and let's call this our distance D1. So good, so if this is 1.5, then this distance has to be how much? 2.5. Good. So this is going to be 2.5 meters. So here, we have a D2 minus D1, which is going to be 2.5 meters, minus 1.5 meters. The last I checked, last I changed math on me, is 1 meter. So good. So now what? So now we know the path length difference is 1 meter. So now.
So since that's like a whole integer, do we already know?
Well, we don't know if that's a whole integer. That's just a number. But keep going with that idea. Good. So what Christian is saying now is that we know this has to be equal to either m times lambda or m plus a half times lambda. And it's this value here that has to be either a whole integer or half an integer. So what that means then is since we know the path length difference, which is delta d, we can find the wavelength and then do what? Divide the path length difference by the wavelength and find out if it's a half integer or full integer. So if it's a half integer, that gives us destructive interference, and if it's a full integer, that's going to give us constructive interference. Good. So since it has to equal one of these two things, what we're going to find out is what is the prefactor which goes here. So we're going to divide both sides by simply the wavelength. So how would I find the wavelength?
Use the speed.
Good. So we know that the wavelength then is going to be equal to the speed divided by the frequency. So let's put everything together. So we want then is the path length difference divided by the wavelength, then it's going to be equal to some number, I'm going to call that n. We want to know is n an integer or is it a half integer? Good. So this is going to be then equal to the path length difference times the frequency divided by the velocity. Okay? Good. So our path length difference is what? 1 meter times my frequency, which is 171.5 hertz, divided by the speed, which is 343 meters per second. Okay. Put in all that. This is simply equal to a half. So this tells me then that the integer, or whatever the prefactor is simply equal to a half, which means that it's actually a half integer, which means that is a constructive or destructive interference. Destructive. So overall, I'm not going to blow up Jasmine's ears. She's going to hear nothing.
So can n be like 0.75? Is it always half or whole?
For us, it's always half or whole. It's a little more complicated to talk about those intermediate type regions. Because in intermediate regions, it's not fully constructive and it's not fully destructive. So it's actually kind of somewhere in between.
Okay.
So this expression that we wrote down, so this one only works for fully constructive and fully destructive. Okay. So these are only the maximum two.
So it can totally happen that n is like.
Right, so if you were calculating, for example, the homework on the exam or something, and you got, like n was 0.46, then you would just call that 0.5 or a half.
Okay.
So then you just say, okay, it's destructive interference. Yeah. Yeah. So technically, yeah, it has to be either a whole integer or a half integer. If you're close to a whole integer or a half, then just round it to that, and then call it that. All right, so that's it. So everybody have a great weekend. It's a long weekend. 4th of July weekend. Don't get in too much trouble. And then I'll see everybody on Tuesday. So we'll do another table of path difference on Tuesday, and then we'll start talking about some other interesting interference patterns and things that we have. Yeah, we called me like